Here's a quick review of partial fractions. So, partial fractions. Okay, so the idea is that we have this wonderful, amazing theorem that says if I have something like x plus 2 divided by x minus 1, x plus 1. So I have a rational function, one polynomial divided by another. It's a proper fraction in that the top has a lower degree than the bottom. Then it says, if I can factor it like this, then I can write that as some constant a over x minus 1 plus some constant b over x plus 1. And now to find that, the basic idea is you actually redo the right side over here, get your common denominator, so multiply the two things together, and you get a times x plus 1 plus b times x minus 1 all over x minus 1 times x plus 1. And so now that we've got these two fractions, the denominators are exactly the same, and so if they're the same, the numerators must be the same. So we have that x plus 2 has to equal a times x plus 1 plus b times x minus 1. And there are various ways to now find a and b. The most formal way is to realize that, okay, over on the left side I have a function, and on the right side I have a function, and they should both end up being these linear functions like x plus 2, and therefore, I can collect like terms, and so I would have a plus b times x, and then plus my constant term a minus b. And, well, this coefficient here on x, 1, has to be the same as that coefficient a plus b, and so we now can write down the requirement that a plus b is equal to 1, and similarly the constant here has to be 2, and so a minus b has to equal 2. Now if I add those two things together, I get 2a, the b's go away, and I get 3. And so a has to be 3/2, and so if that's the case, then b has to equal negative 1/2. And so that means that my x plus 2 divided by x minus 1 times x plus 1 is equal to 3/2 over x minus 1 plus a negative 1/2 over x plus 1. And we could check that out, but hopefully it should work just fine. But that's the basic idea. Now, other ways to deal with this are that, okay, here, as I look at this whole thing, on the left I have a function, on the right I have a function, and for two functions to be equal, they have to be equal for all values of x. And so we want to have this be equal for all values of x. So way back here, when I'm thinking about just the numerator part, the 1x plus 2 equals a times x plus 1 and so forth. Let me rewrite that down here. I've got x plus 2 is equal to a times x plus 1 plus b times x minus 1. Okay, so I have those two pieces, and they have to be equal for all x, or the functions aren't equal. Well, I could choose various values of x, and so for instance, notice if I let say x equals 0, I would get 2 equals a minus b. So there's one function, and if I let say x equal 2, I would get 4 equals 3a and plus 2b. And once again, I can do something like, let's see, did I do that? Let's say I let that equal 2, so that's a 3, oh, 1b, sorry. Something looked wrong there. So 2 minus 1 is 1, at least on Wednesdays. And so again, I can, add these two equations together to get rid of the b's in this case, and so I get 6 equals 4a, which tells me a is equal to 3 halves, and then I can go up here and use the same a minus b equals 2 to get b is equal to negative 1 half. So the same answer. And then even better, and this is where I think there's sort of magic in all this, is I happen to choose x equals 0, which seems like a nice thing to choose because 0 is always nice to work with, and then x equals 2. But notice if I chose x equal negative 1, on the left-hand side I would get 1 equals, but by choosing x equal negative 1, this x plus 1 turns into a 0, so a just plain disappears, and I get that I have negative 2 times b. Well, immediately that tells me b is equal to negative 1 half, and then if I let x equal 1, the thing that zeroes out the b here, I get 3 is equal to 2a, and so that tells me right off a is equal to 3 halves. So a judicious choice of x can lead to very simple equations to solve, and that's often the way I attack this. But this is where I just find this quite amazing, because up here at this equation, that doesn't look like a big deal to say, well, of course, sure, let x equal 1, or let x equal negative 1 to get rid of that part. But remember where this came from. It came from this idea up here, is that we had a fraction here for which x equal 1 and x equal negative 1 are not even defined, and yet it works. So it's kind of a magic thing here that you can use those particular values of x, but actually you can, and so that's one way to do it. So again, the formal way, the formal way is to just go ahead, write your fractions, and then match up like terms, and by matching like terms we end up with simultaneous equations, and we should have the right number of equations with the right number of unknowns, and we go ahead and solve that. But again, a less formal way to look at it is that on those numerators, those two functions have to be the same, but if two functions are the same, then every value of x I pick should work to make this thing have an equality. And so that's what I did in these two cases down here. I chose different values of x in each case, but it still works. So whatever values of x I pick, it will work. There are just some values that make my life a little easier than others. So that's our first part of partial fractions. And we'll stop there, and then I will do a little more on partial fractions.